Dear students, let us discuss basics of antenna theory, right? Actually, antenna derivations are like this, but I told you no use of doing derivations. But antenna derivation procedure is like this. The antenna derivation procedure is first current distribution is given. Current distribution given in the antenna, given I. Then what you do if current distribution is given, we will be finding vector magnetic potential. So this is actually vector magnetic potential. So first we will calculate vector magnetic potential. The formula of that integral mu I dl, actually wherever this current conductor is there, that is taken as 0.1. So mu I1 dl1 bar divided by 4 pi modulus of R12. 0.2 means at which location you want A12 bar, otherwise E12 bar, H12 bar. So that is that point. The unit of this is Weber per meter, dear students, right? Once if current conductor location is given and current distribution is given, then at point 1 location this current conductor is there, you will be selecting at point 1 location small length vector. Then at point 2 location you want the vector magnetic potential. So R12 bar is nothing but 0.2 minus 0.1. So after that we will be finding A12 bar by integrating. Once if this is calculated, then you know B bar is equal to del cross A bar in terms of vector magnetic potential. That means A12 bar means vector magnetic potential at 0.2 location due to the I1 current conductor is present at a 0.1 location. Now B is equal to mu into H. So from this magnetic field is calculated. How much magnetic field is generated from the given current, it is calculated. Actually, why to calculate first vector magnetic potential? It is the simplest quantity, no cross product, no whole square here, so it is easy to calculate. Then after doing cross product by dividing with 1 by dividing with mu, we get H bar. Then if you know H bar, then del cross H is equal to sigma E plus epsilon dou E by dou T. It is time domain. And del cross E, because for example if there is antenna here and it radiates into the air, for air medium sigma is 0. So del cross H is equal to this is 0. J omega d by dt means epsilon E s bar, and del cross Hs is the determinant. You will be substituting this vector in the determinant, then from that you will get Es bar. So after that you will be finding average pointing vector, that is half into real part into Es cross Hs star, then watt per meter square. This average pointing vector you get. Then power radiated is equal to average power radiated is equal to units watt. So average pointing vector dot ds bar you will be taking. PAVG bar is watt per meter square, multiplied with meter square you get watts. So this is the procedure actually in antenna derivations, but there is no use of doing derivations, I told you. And dear students, what is the use of antenna? For example, if you take here generator, then here internal impedance, okay, then here transmission line is there. What is the use of transmission line? For example, FM signal is there here, radio mirchi signal, okay students. Now it is transmitted through the transmission line. where up to the antenna. Now here is the antenna. These conductors are bent in shape. Actually, the same conductors can bend. So they are in this shape, for example. Okay, this is antenna. Now this antenna is a device used to match the impedance of this transmission line and the air medium, that is eta is equal to 120 pi. That is one purpose. For example, if you don't use this antenna, then here open ends are there, then here impedance and this air impedance are not matched, so the total signal is reflected. You can't radiate into the air. So if you put antenna, then it tries to match the impedances of this medium and this one, so that it radiates the power. So one purpose of this antenna is to match the impedance of the transmission structure and the impedance of the surrounding medium, that is air medium. So for impedance matching it is used. That is one thing. Second thing is for efficient radiation of the EM energy. For example, if you ask this open end transmission lines to radiate, just like that they radiate. In which direction we do not know, but actually you know in which direction, but the thing is in the desired direction they cannot radiate the EM energy. So if we have antenna, if antenna has gain, antenna has directivity means in particular direction we can radiate without wasting the energy. For example, here people are there, they want to listen the radio, you can particularly radiate in that direction, but no need to radiate in this direction if nobody is there. So it is wastage. So directivity is there means in particular direction you can radiate the signal. In particular direction you can radiate the signal, dear students. Okay. So that means that is called efficient radiation. You can increase the gain and you can transmit. You can because of directivity in particular direction you can radiate. Those advantages are there because of the antenna. Next, students. Actually, here there is a conductor and current is there, and that current goes here like this. Now here there is no conductor. Now current passes in a closed path. Here air medium is there. We have studied already in the static fields, but some students might not have heard of static fields. Don't worry. Here I wrote this equation, you can see here. So this is a del cross H is equal to current density. This is called displacement current density. So JD of T is equal to dou D bar divided by dou T. So epsilon dou E bar by dou T. That means in this medium epsilon is present, because of that also current goes. So that is called ID of T, displacement current. So there is a displacement current because of electric flux that will be passing here like this, like this, like this. So here conduction current is there in the conductor. Here displacement current will be there like this. So ultimately again current will be here like this, conduction current here like this. So these conductors start radiating the EM energy at high frequency. The meaning is that in a conductor DC current is transmitted, no, disturbance is less, and if AC current is transmitted, no, disturbance is more. If high frequency AC current is transmitted, no, disturbance is very very high. That conductor tries to expel that current signal out of the conductor. So in that way radiation starts actually. So now this signal keep this current keep going like this. At the same time it tries to pass in a closed path. At the same time some amount it starts radiating into the surrounding medium and air medium. Okay, actually whenever it has some frequency, Air current is going, na, that has some frequency. Then it has some wavelength, V by F wavelength. If the medium present between the conductors, transmission line conductors, has some epsilon r, then lambda is equal to C by root epsilon r, V is F. If it is air medium, then epsilon is 1. So it has some wavelength for the signal. Then whenever physical length of this antenna approaches lambda by 2 wavelength, then they observed it starts radiating. That means at that at this condition, the disturbance in the conductor is very, very high. So dear students, so disturbance here means high frequency signal. I will tell you one example which you can see with your eyes. आप आंखों से देख सकता है. You take a stone and this is water actually. This is water tub. पानी का टब है ये, ठीक है. So here water is there. You take a stone and hit that with forcefully. Throw that stone here. So you are throwing that stone means that stone has so much energy, kinetic energy, that has some energy. So the moment it hits the water particles, then lot of disturbance is there in water particles. They start disturbing. Now these water particles disturbed at this location. Now these water particles tries to send that disturbance away from that location in the form of tides, TIDE, tides. So it start going like this. So here energy is given suddenly, that means disturbance is there. Then in the form of tides that goes onto the surfaces, then again it disappears. Again you hit the horn, immediately keep hitting. Then these water molecules start sending that energy away, and they try to release that energy. Similarly, these conductors also very high frequency signal is very high frequency signal is connected. Then disturbance is very high. Those conductors cannot handle that high frequency. They try to send that high frequency signal out of the conductor. Okay, they observed that whenever the frequency is for example F, then calculate lambda, then physical length of the antenna is approaching lambda by 2, then they started radiating, student. So here the purpose of the antenna, first one is to match the impedance of the transmission structure. That means that transmission structure could be coaxial cable, okay, two-wire transmission line, coaxial cable, short name is coax, waveguide it can be, they are called transmission structure. And the surrounding medium into which EM wave is or otherwise EM energy is EM wave is radiated. One example I told you already, did you remember? For example, if there is a rectangular waveguide carrying some energy, so this has some impedance eta G, guide impedance. Now here input is given, you want to radiate into the air. Now air medium has 120 pi. Now eta G you get different value, eta naught, for example air-filled rectangular waveguide, then eta G is equal to eta naught divided by root of 1 minus Fc by F whole square. That eta naught is 120 pi actually. So 120 pi this one, but this is 120 pi divided by something, it may be more than that. Then that's why what we do here, we start opening these ends. If we start opening these ends, then automatically what do you say, you open these ends, so that whenever A and B dimensions are changed, then this eta g gradually changes, so that whenever the eta g of this waveguide, you keep opening the ends, then whenever impedance of this waveguide due to change of dimensions approaches this 120 pi, then the waveguide dimension is cut there, then so it easily matches this impedance and that impedance. Now this is called horn antenna, HORN, horn, horn antenna. So impedance matching is done. So that's what the statement here. Antenna is used to match the impedance of this transmission structure and the medium impedance and into which this EM energy is radiated. And also for efficient radiation purpose of EM energy, I told you in whichever direction you want radiation, in that direction only it radiates by using the directivity property. So the purpose of the antenna is to radiate EM energy, efficiently. That means a lot of meaning is there here. Efficiently means without loss, and also in particular direction, and by adding some gain. A lot of meaning is there. Anyway, this discussion nobody will ask you in examination till now. Whatever we have discussed, there is no use of this discussion. Okay. Exam preparation is different, telling stories is different. Now let us go to the, I will talk little more, then we will go to the exam mode of preparation. Okay, my dear students, first let us talk of Hertzian dipole. It is also called as infinitesimal. Infinitesimal means very small, student. Infinitesimal means very small, that is dictionary meaning. Infinitesimal dipole. So Hertzian dipole antenna, you can say simply Hertzian dipole, you can say infinitesimal dipole antenna, you can say, or otherwise simply infinitesimal dipole, you can say. Okay, so antenna, Hertzian dipole, or otherwise Hertzian dipole antenna. Here, what is this Hertzian dipole? It is a conductor rod like this. This is a plastic pen, but similar to this pen, cylindrical rod, this is exactly similar to this conductor is taken. Instead of plastic, plastic का place में conductor लेता है ऐसा. This is conductor rod actually. Now the length of that is taken as a DL, you call, or otherwise sometimes it is called as L length only. It may be DL or otherwise L you can call, but the condition is DL is less than or equal to lambda by 50 for uniform current distribution it is taken. So here the length is taken as a L also you can take, or otherwise DL also you can take. So let us take this length as DL, this length DL length. Now actually if you want to find the electric field equation, you must consider the coordinate system. You must put this antenna at some location. You have to measure the field at some other location. That means you must take the coordinate system. So this is y axis and this is x axis and this is z axis. and this the antenna, infinitesimal antenna, that means very small length antenna, is at the origin now. That means the source location is origin. So if you want electric field here, or otherwise magnetic field here, or otherwise average pointing vector here, so any quantity you want here, then it looks like a point source, point, very small, so it looks like a point source. Point means actually from far distance, if you see from 1 kilometer, 2 kilometer, it looks like a sphere. It won't look exactly like a sphere, but it is considered as a sphere because very small. I am trying to explain you why it is solved in spherical system. Because any shape of antenna, if antenna is there, it radiates energy, then after 5 kilometer, 10 kilometer, you will be going and talking. So for that location, that antenna can be considered as a point source. So problems are easily solved in spherical coordinate system. So anyway, now in spherical system, point r comma theta comma pi location is general location which can represent which represents all locations in the universe. Now at this location, from the origin, at this location you will be measuring the electric field quantity, magnetic field quantity, and they are functions of r theta pi, h bar, e bar, like that. Okay. Now this is z axis. What is the name of this? Line drawn from center of the antenna to the field point. This is called field point. That means point means the location where you are measuring the field quantities. So the angle between the z axis and the line drawn from center of the antenna to the field point, otherwise angle between z axis and line drawn from origin to the field point, this angle is theta, vertical angle, or elevation angle. Elevation means height. Now distance from here to here is small r. Pi is horizontal angle or azimuth angle. Now here in this antenna conductor, in this direction, if you send the current like this, I0 current, some books I0 or otherwise some books they write IM. That is magnitude of the current, that is uniform current. Uniform means what, student? It is not a function of distance. That means at any height this current value is constant. Uniform current, I0 uniform current is given to this, that is called excitation. Excitation means giving input. So I0 or otherwise IM, that is maximum value, I0 or otherwise IM, uniform current is given to this. Uniform means what, student? Not a function of distance. Not a function of distance means what? At any height you will see that current only, constant current you will see. So here you can write like this also, In I0 cos omega t. You can see it is not a function of distance. It is called uniform current. It is not a function of distance. Be careful. Time is different. Already beginning I told you. Uniform means what? Anything is not a function of distance, that is called uniform. So time is different, distance parameter is different. Right. Now the way I told you the procedure, given current distribution, then find vector magnetic potential, then find H is equal to 1 by mu del cross A, then we can find electric field, etc., etc. That is the procedure you will be in the textbooks they solve. Now without solving, we will write the equation and we will start analyzing the equation. Dear students, here there is one conductor of length dl, that dl is less than or equal to lambda by 50, it is taken. That is called as infinitesimal dipole antenna. The current distribution is uniform current, constant current, I0 or otherwise IM in some books they write. Now put the thumb in current direction. If you put the thumb in current direction, then a magnetic field generated due to that is in circle direction. Which direction? Circle direction. It is in circle direction. So circular means what? We are solving in spherical coordinate system, and horizontal circular is pi direction. Which direction? Pi direction. That means magnetic field has pi component in this case. So if current goes in z direction, then according to right hand thumb rule, in the closed finger direction magnetic field is there. That magnetic field is circular, horizontal circular, that is pi direction. So h pi component is there here. So that h pi component, S means in steady state or otherwise phasor domain, is equal to I naught, that is the current distribution, dl sin theta, theta means angle between z axis and the line drawn from origin to the field point, divided by 4 pi, you get this one, j beta by r plus 1 by r square e power minus of j beta r. I did not put this in the box, you are not going to remember this. एक्चुअली ऐसा आदत है, कुछ भी इक्वेशन लिखेंगे डब्बा रख देता है. नो, मेरा पर्पस है, फैकल्टी का पर्पस है, that I have to tell the students what is important, what is not important, what to study, what not to study. Okay, so don't put that in the box, student. Here if you see, let us talk of unit, student. This current generates magnetic field, I naught is there, then dl is the length of that, theta is angle between the z axis and this line drawn from origin to the field point, then r is distance from origin to this field location, beta is 2 pi by lambda, then e power minus j beta r. You have seen e power minus j beta z matlab kya hai, student? Wave is traveling in z direction. Here e power minus j beta r means wave is traveling in r direction, radial direction. Because I told you, no, this is like a point source. Point means sphere. Every direction radially it radiates like this. Radially it radiates energy, e power minus j beta r. It radiates, but I am not telling in every direction it is same amount of magnitude, because angle changes, the value of this also changes. In different angles, different magnitudes are there. So if EM wave goes in r direction, power also goes in r direction. That means unit vector in power direction is AR cap, AR cap. So you remember that one, AR cap means this one. Unit vector in power flow direction is AR cap, because wave is traveling in r direction. Now you see the units, e power exponential, e means 2.71, no unit. Beta is actually radian per meter into meter, no unit. 1 by meter square. Here this is a radian per meter beta divided by meter. So radian per meter square. 1 by meter square plus 1 by meter square should be there. Right? Next 1 by meter square is there here. Then I naught means ampere. I naught means ampere. DL means meter. Sin theta no unit. So this is the unit. 4 pi no unit. Meter gone. And ampere per meter is remaining. Okay. Electric and magnetic fields are perpendicular to each other. Here total number of components are directions are r direction, theta direction, pi direction. If H has pi direction, then automatically electric field is perpendicular to the magnetic field. Then electric field will have r component and theta component. Now already I told you, if you substitute this in del cross H is equal to j omega epsilon E, so epsilon ES bar in this formula, automatically you get the electric field equation here, because it is air medium. For air medium, sigma E, actually del cross H is equal to sigma ES plus j omega epsilon ES bar. So sigma for this air medium is 0. Now after substituting in this equation, you get electric field theta component in phasor domain, and first r component, electric field in r component in phasor domain, and electric field theta component in phasor domain you get. If I write electric field theta component, dear students, here na, electric field has theta component divided by electric field by magnetic field is equal to eta, and here for air medium it is eta naught, student. That means E by H na. So you want E is equal to eta naught into H. So this is H and you have to multiply here, eta naught also should be there. So after doing derivation na, after doing derivation you get eta naught I naught dl sin theta divided by 4 pi, and this will have j beta divided by r plus 1 by r square minus j by beta r cube, you get e power minus j beta r you get. Here one more term added, no problem. You can see the units of that. J no unit, beta means what, student? Radian per meter into meter cube. Radian per meter into meter cube gives denominator meter square. This is also 1 by meter square. Radian per meter by meter, so it's also meter square, 1 by meter square. So units matched. Now here this is you get eta naught I naught dl cos theta, you get here cos theta divided by 2 pi, and the terms are 1 by r square and minus j beta r cube, you get e power minus j beta r. No need to remember any equation I am telling you. Even if you remember them, no use for examination. No use for examination. Keep watching. देखते रहो. So dear students, मैंने देखा था एक फैकल्टी पढ़ाया था इसको, उसमें फार्मूलाज हेडिंग रखा, फार्मूलाज सब लिख दिया रट के, वो डब्बा में रख दिया, बच्चे लोग मर जाएंगे पढ़ के, कोई फायदा नहीं है. एक्चुअली एग्जाम प्रिपरेशन मीन्स व्हाट इज रिक्वायर्ड फॉर एग्जाम. एग्जामिनर का नर्व पकड़ना है, वो है टॉप 10 में निकलेगा स्टूडेंट्स. बिकॉज आई हैव रिटन सो मेनी एग्जाम्स, सब में टॉप 10 है. और BHL में काम किया था, बोला था आपको, और इंजीनियरिंग सर्विस में ऑल इंडिया 4th रैंक थे. हम बीटेक में पूरा रात भर पढ़ते थे और कोचिंग नहीं लिए थे, ओन पढ़ते थे. ऐसा पढ़ते थे, फिर रिकॉल करते थे. रिकॉल करने के समय में सोचते थे कैसा वो लिख दिया, क्यों ये आया, कैसे आया, ऐसा. सो इस तरीके में इंटरेस्ट के हिसाब से पढ़ लिए थे. ठीक है, कोई बात नहीं है, आपका टाइम ज़्यादा प्रीशियस है, बात नहीं करेंगे. लेट अस गो अहेड स्टूडेंट्स. नाउ I wrote this and I wrote that. Later on I wrote this because this equation is going to die. वो मर जाएंगे वो. Let us see why. Actually students, if there is one antenna here, na, for example, near the antenna at r is equal to 0.1 meter, that means r is equal to 10 power minus 1 meter. Students, I want to see this value, student. Then at r is equal to 10 power minus 1 meter, if you see these values, 1 by r value, 1 by r square value, 1 by r cube value, and this is still further I have to reduce like 10 power minus 2 like that. So this is 10 power minus 2, that means very closer to the antenna, that meaning is. Then 1 by r means 10 square, and 1 by r square means 10 power 4, and 1 by r cube means 10 to the power 6 actually, students. So r is equal to 10 power minus 2 means you are trying to calculate the fields very closer to the antenna. Then in that case, this term 1 by r cube term has highest value. You see here 1 by r cube term, here is there, here is there, here it is not there. That means meaning is that first magnetic field is negligible near the dipole conductor. That means this term, actually student, very closer to the antenna, only this term is considered. These two are neglected. If you neglect these two, this is not there, a magnetic field is not there at all. then this is gone, these two are gone, only this term is there. Only electric field has a radial component and what do you say, theta component. Only electric field is there, students. That means very closer to the antenna, only electric field is there. What is the meaning of that, you know? Near the antenna, medium is there. First in that medium, epsilon is there, permittivity, that receives the energy into that. Because this antenna is ready to radiate in the air medium, this epsilon mu are there and they don't have energy. It is network theory, student. In the network theory, LC circuit is there, and if C, capacitance is not having energy, that is ready to receive energy. If inductor is not having energy, that is ready to receive energy. If a capacitor has energy, that is ready to release energy. If inductor has energy, that is ready to release energy, like that. So if capacitor has some energy, it is ready to release. Inductor is not having energy, it is ready to receive. Then it receives energy. Then again inductor has energy, it is ready to release. And capacitor is not having energy, it is ready to receive. That is the nature of the law. Uparwala hai wo, Bhagavan. So students, again it receives. So it keep changing, that is tank circuit. Same way here also. First, there is energy in this conductor in the form of current that is ready to radiate. Now in the air medium, epsilon receives that energy first. If epsilon receives means only electric field receives energy. That's what these equations are saying. So that is why at the beginning magnetic field is not there. So that is why this term is this has very high value near the antenna. That means only electric field is there. So that is why this term is called as 1 by r cube term is called static field term. Static field term. Static field means what? Static electric field cannot generate magnetic field. Static magnetic field cannot generate static electric field. That means there is no interaction between them. That is the meaning. And if you see carefully, I did one derivation in the static fields. GATE students might not have seen that. For dipole, no, electric dipole, electric field was proportional to 1 by r cube. Dipole has a positive charge, negative charge. They are static charges. Then static electric field came. The electric field was proportional to 1 by r cube. That is why 1 by r cube term is also called as static field term. No problem here, students. So in examination they will ask you, I will write that 1 by r cube term is called as static electric field term or otherwise very near field term. Both names are there. Static electric field term or very near field, that is called. Now let us go to the far field. For example, if I from the antenna, if I go to 1 kilometer or otherwise 10 kilometer, then that is nothing but 10 power 4 meter. This is 1 by r, this is 1 by r square, this is 1 by r cube. This term becomes 10 to the power minus 4, and this term becomes 10 power minus 8 at this distance, and this term becomes 10 power minus 12. That means this has least value. You can neglect this, you can neglect this. This only you have to consider. At least you have to consider some term. No? This term you will be considering. So this term is having highest value at far field. Far means at higher distance. Dur mein. So it is called far field. Far field. It is called far field. This is called very near field. Very near to the antenna. Or otherwise I told you, whenever you take this term, then automatically this present, this is neglected, because 1 by r square and r neglected, this is neglected. Only electric field is there. That is why it is called, it is also called as static electric field region, or otherwise very near field it is called, because r is very small, so very near field, or otherwise only electric field is there, static electric field is called. Here is r 10 kilometer from the antenna means it is very far, so that is why far field it is called. Whenever you neglect 1 by r square and 1 by r cube at far field, what will happen, students? This is gone. Both terms gone. 1 by r square, 1 by r cube, neglected. Both terms gone. ERS gone. Then h pi s only present. Only one term. And these two gone. Only this is present. Only E theta s is present. Have you seen what is happening now? Implies E theta s divided by h pi s is equal to eta naught, that is 120 pi. That means at far field, electric field theta component generates magnetic field pi component. Magnetic field pi component generate electric field theta component because of air impedance. That means these two components generate each other. That is called radiation, electromagnetic radiation. Radiation means convert electric field to magnetic field to electric field, so that energy keep going. How? I will show you here. So epsilon energy change to mu. Then I told you, if mu is field means energy is in inductor. Then beside that again epsilon will be there, that is empty. It is ready to give, so it is ready to receive. Energy goes here. Then beside that again mu is there. It is ready to receive. It is ready to give. It goes here. Again epsilon. It goes here. Keep going energy. You are here with your mobile phone, and it gets signal like this. It is getting students. You will be listening that. So here what is happening? Radiation is happening. Electric field converted to epsilon means electric field. Magnetic field, mu means magnetic field. E converted to H, like that they keep exchanging. That is called radiation field. What field? Radiation field. You can see here now. Pointing vector is equal to E bar cross H bar. So E bar means only theta component is there. E theta, A theta. H bar is H pi, A pi. Now E theta, H pi, A theta cross A pi is A r cap. That means power is flowing in r direction. Yes, it has to flow because wave traveling in r direction. So at far field, only E theta and H pi components are there. Electric converted to magnetic field, magnetic converted to electric field. They keep carrying the power. That is the meaning of radiation. What is the meaning of radiation? Electric field converted to magnetic field converted to electric field. So you are here now standing. Then here coming time varying electric field, change it to magnetic field change it to electric field. Like this, here you will feel that radiation मिलता है आपको. So whenever that EM wave enters into your body, then that has some energy. That energy hits your body cells, and the body cells are killed if that is high energy. That is why that is the effect of EM radiation. So far field or otherwise radiation field it is called. I will write in the note. Just I am making you to answer. Students, just very near to the antenna only electric field was there, that is called static electric field or otherwise very near field term. First time, pehli bar, electric energy is transferred to the magnetic energy. First time that happens. First time. After that it keep changing. Then first time electric energy transferred to magnetic energy. That means first time energy transferred from epsilon to mu. That is called induction field. Induction. First time that is happening. So that happens in the middle region. So that is called induction field, or otherwise is also called induction term, or otherwise near field. Near. It is very near. Next comes near. Next comes far. So now I have answered one objective question. What is that objective question? In these equations, 1 by r cube term is called, two names are there. One name is very near field, or otherwise static field term, or otherwise static electric field term. Second one, 1 by r term, 1 by r square term is called near field. Remove the very remove. So near field or otherwise induction field. Third term, 1 by r is called as a far field or otherwise radiation field. Always we do calculations like average power radiating, etc. Always we do calculations at far field, because there is antenna. You will never go to the antenna, and near the antenna you will not talk. You can't carry the antenna with you to transfer the signal. It is far away. So that is why this is more meaningful. Next, I am going to give you the distances calculation formulas, so that I will write, so that we will go ahead, students. So now in the note, you don't write all these things. So in the note, you write the names of these fields, because the subject is very complicated. If you start analyzing, it will take a lot of time, but you have to study this in controlled way. Control should be there, student. Control रहना इसमें, नहीं तो टाइम बहुत खा लेता है ये. So dear students, here 1 by r cube term is called as static electric field term or very near field term. Second one, 1 by r square term is called as induction field term or otherwise near field term. Okay. Third one, 1 by r term is called as radiation term or otherwise radiation field term, or this is very near, this is near, this is far field term. Have you seen very near field, far field? Or otherwise here in terms of electric fields, static electric field, induction field and radiation field. Radiation field means E and H start producing from each other. E converted to H, H converted to E, like that. So this one you have to put this in the box. You have to read this. Now what is important to us, dear students? Far field is important to us. So at far field, 1 by r cube comma 1 by r square terms are neglected because they have very less values. Now in this case, 1 by r square and 1 by r cube term neglected, this is gone, ERS, and only this is present. Now H pi s becomes I naught dl sin theta, divided by 4 pi, then j beta divided by r, not r cube, r is there, and e power minus of j beta r. So you remember this one. You have to remember this one. So students, here we have, that means E theta s divided by H pi s is equal to eta naught, and if you know H pi s here, then you know that that is why E theta s is equal to eta naught into H pi s. Okay, so E by H is equal to eta. If you want the electric field, then take H pi s and multiply with eta naught. Okay, students. So, and here, if you remember this equation, no need to remember the electric field equation at far field. Anyway, for objective questions, they may not ask this also, but for conventional questions, you need this. We will be talking of that one. Okay. So, students, we have seen the magnetic field intensity pi component. You have remembered. I told you to remember. Then E theta s divided by H pi s is equal to eta. Then E theta s is equal to eta into h pi s. Now, what else are required for examination? For example, if this is the Hertzian dipole, then this is a diameter, this is actually a height, then largest dimension is called d here, largest dimension. For example, if this is the antenna, this is width and this is height, this is length. Out of three dimensions, this is the largest dimension, where d is the largest dimension of the antenna. I will write that there. Now, if we send current in this, then EM waves are released here. In this, up to some distance like this is actually sphere here, like this. So, up to some distance from the antenna, let us say radius is R1, and let us say this radius is actually R2. Now, here R1 is equal to 0.62 root of d cube divided by lambda. You can see the units. This is meter cube by meter, root of meter square is meter. This is R1 distance. If there is antenna here, up to this distance, very near field exists, or otherwise static electric field exists here. So, this is a very near field. Now, from R2 to from R1 to R2 distance, you have this one induction field. This is also called Fresnel zone. So here R2 is equal to 2d square by lambda. This is called induction field. This is called induction field. This is also called near field. This is also called Fresnel zone. Now, here R radius greater than or equal to this one 2d square by lambda. This is called far field or otherwise radiation field. Far field or otherwise radiation field. Far field or otherwise radiation field. So, these things you have to remember, students. Here D is largest dimension of antenna. Largest dimension of antenna. Here lambda is equal to V by F, that is C by root mu r epsilon r F. Okay, C by root mu r epsilon r into F. If around this air medium is there, then you have to put C by F simply. These things you have to remember. I told you na, this is 1 by very near field means electric field term dominated is 1 by r cube term. This is the here 1 by r square term, here 1 by r term. So these distances you have to remember. This is in note actually. This is in note from here to here. Far field is to be measured at the distance r is greater than or equal to 2d square by lambda. This is called as This is called as Fraunhofer condition. Okay, Fraunhofer condition, this one. Right. Now, whatever discussions we do, whatever formulas we do now from now onwards, they're all for far field zone only we will be discussing. Right. Now, here I want to tell you one thing. For example, this is transmission line. This is the antenna conductors are there here. This antenna conductor has a RL. This is called loss resistance. This is called loss resistance. Okay, we will talk of that later on. Similarly, this antenna radiates power. So how much power is radiated, that is decided by radiation resistance. So actually students, it is like this. In network theory, average power is equal to half into Im square, half into Im square into R. That is maximum value. If RMS you write now, then I RMS square into R. Now here actually how much power radiated, that is equal to half into maximum value of the current whole square into, so this one is radiation resistance, same formula. Now from this uh, if you know the maximum current and radiation resistance, then how much power is radiated by the antenna, you can find from this formula. So for that purpose in examination they give the current value, but radiation resistance value you have to decide that one. Now that radiation resistance we will write here. So anyway, if loss resistance we will talk of that later on. So this antenna conductor, now whenever current goes in this, there are heat losses. Those heat losses are decided by this loss resistance RL. Whenever you give, whenever you supply electromagnetic wave to this antenna, then it radiates power. How much power is radiated by that antenna, that is decided by radiation resistance of the antenna. Actually, if any antenna has infinity radiation resistance, then total power is radiated without loss, but that is theoretical discussion, it won't happen. So now this formula I will be putting in the box later on, and if you want power radiated, then radiation resistance is to be known, and the power radiated and Im is given, then also you can find radiation resistance. Okay, so that formula you write here. Average power radiated by the antenna it is called as P radiated, is power radiated is equal to half into Im square. Actually sometimes this Im is also given as I naught, so you should not confuse, that is the maximum value of the current actually. Okay, I naught square students, half Im square R radiation resistance, and some books Im is given as I naught, so this one. Now this this is watt, unit is watt. Okay, this you have to remember. So where Im is maximum current, maximum current, Im or otherwise I naught. Okay, I naught or Im, both are same. So I naught or otherwise Im, that is maximum current, that is. This one is radiation resistance, radiation resistance, ohm, radiation resistance of the antenna, radiation resistance of antenna. Okay, radiation resistance of antenna. It is like simple network theory, and you need not to worry about that one, right? Now we have to write the radiation resistance of this Hessian dipole antenna. Actually, in the Balani's book by antennas, it is written, they have written two different formulas, but Sadiq book, they write a different formula. Anyway, what they are telling, I will write here. You note down carefully. For DL less than or equal to lambda by 10. Okay, this is given in the Sadiku book. Of course, same thing is given in the Balanis also, but I will tell you. For a DL less than or equal to lambda by 10, Hessian dipole or otherwise infinite simal dipole, Hessian dipole antenna, radiation resistance is equal to 80 pi square dl by lambda whole square ohm. Okay, this is the formula. If I naught uniform current, if I naught uniform current means constant current in the entire height of the antenna. So uniform current is present along the length of the antenna. Okay, but what Balani book says, if the length is a little more, it is difficult to maintain the uniform current or otherwise constant current. This uniform current is also called as constant current, so not a function of distance. So it is difficult to maintain the uniform current if the antenna length is more. In that case, automatically it is approximated as a triangular current distribution. For that, this radiation resistance becomes 20 pi square dl by lambda whole square, and length is also mentioned. And for small dipole, or otherwise it is also called as a short dipole of length lambda by 50 less than dl less than or equal to lambda by 10 of length this much, having triangular current distribution, that means I is equal to I naught, this is called I of z, is equal to I naught 1 minus 2 mod z by L ampere, this much. Okay, this is a minus, I have taken dl means I will take L here, friends, L, because if I take dl here also I have to put dl by 2. So if I take L here, then minus L by 2 less than or equal to Z less than or equal to L by 2. That means 0 to minus L by 2, here mod Z is to be replaced with what do you say, mod Z is to be replaced with minus z here, so that it becomes minus into minus plus, and for this distance it is replaced with plus. So anyway, no need to remember this one. For a small dipole or otherwise short dipole of length L is between lambda by 50 and less than or equal to lambda by 10, then Balani book says it is difficult to maintain the constant current in entire length. Automatically that current distribution is approximated as a triangular current distribution. Then in that case it becomes a 20 pi square. 20 pi square. But this statement is not read by the some examiner question. Some examiners also just like that, without giving data, just like that they ask the question. So that is why there is a problem for the students actually. Okay, anyway, so triangular current distribution, put this in the bracket, no need to remember this one, is current distribution is radiation resistance is equal to 20 pi square. Here I wrote L, so L by lambda whole square. If I write dl here, here also dl by lambda whole square, then dl by 2 minus dl by 2, dl by 2, like that you will be writing this many ohms. Okay. Now this one. So in examination, if triangular current distribution is not given, then for this range also, if uniform current distribution is there, then for this range also formula is this only, student. So for I naught uniform current distribution, that means at every location current is I naught on the length of the antenna. So this is the antenna rod, then here also I naught current, here also I naught current, here also I naught current, that is called uniform distribution. Triangular distribution means if there is antenna like this, then this is z is equal to 0 and this is z is equal to L by 2, then this is z is equal to minus L by 2. Here current distribution is changing like this. The meaning of this is at this location current value is this much height, at this location current value is this much, at this location current magnitude is this much magnitude is there. Current magnitude itself is changing along the length of the antenna. So that is called triangular current distribution. So dear students, if it is mentioned the triangular current distribution, then you have to use this one, 20 pi square L by lambda whole square for this range. Okay, right. Now let us talk of, see, in many questions they give length of the antenna in meters. In that question they give frequency also. Then you have to take the ratio of length and lambda. Then you find length of the antenna in terms of the wavelength. For example, you get lambda by 10, and in the question it is given a uniform current distribution. You have to use this 80 pi square dl by lambda whole square. So in the question, if triangular current distribution is given, you have to use this one, radiation resistance. Okay. Now let us talk of half wave dipole antenna. Half wave dipole antenna. Actually here half wave means half wave length. Here dipole means two rods are there. It is given like this. So this is one transmission line here. This is a transmission line. Now here ZG, VG is there. Okay. Now here antenna rods are there, and here one more rod is there. This is called, each rod is called one pole, two poles are there, so dipole, and this is of length lambda by 4, and This is also length lambda by 4. Overall length is actually lambda by 2, this one. So for this case, I already told you that if current goes here like this and it will be coming like this, so this is displacement current is there here. Once again in this I current goes like this, and whenever this IC conduction current change it to ID, and again it comes back, but at the same time it is high frequency current, it start radiating also, okay, into the air. Now for this half wave dipole antenna, radiation resistance formula you have to remember, and input impedance formula you have to remember, and also magnetic field at far field you have to remember. So at far field, at far field, that means only 1 by r term is there. Then once again this is you say z axis, then once again it is z axis, and if current is in the z direction, then magnetic field is in pi direction. So h pi s is equal to j I naught cos of pi by 2 cos theta divided by 2 pi r sin theta e power minus of j beta r ampere per meter. So this is the h pi s h pi s component. If you want mod, this j will not be there. So you can see here I naught is there ampere, and this is per meter, and these terms doesn't have units. And this one, if you take mod e power j theta mod becomes 1, that one. So you have to remember this one, student, because no, many times they give this angle, they give this distance, and they give I naught also. They ask you to calculate the magnitude of the magnetic field, then from this you can calculate. And if you remember this one already, you know that E theta s is equal to, if air medium is there here, and then that is impedance is eta naught for air medium, so E is equal to eta into h, so that is eta naught actually. Okay, this formula you have to remember. And radiation resistance formula also you have to see. The radiation resistance formula, dear friends, here I told you antenna is a device. Antenna is a device. The input impedance of the antenna here, that means input terminals, the antenna input impedance has a real part as well as a imaginary part. That imaginary part is called reactance part. That is not useful in radiating the power. That simply stores the energy here in the form of epsilon and mu, and again it is given back actually. Okay, so now if you see that radiation resistance of that radiation resistance of this is equal to 73 ohm. This you have to remember. This is for lambda by 2 antenna radiation resistance. This is now the input impedance of lambda by 2 antenna is Zin of lambda by 2 is equal to radiation resistance. So radiation resistance is 73 and J 42 point, the value is J 42.5. So this one is radiation resistant, and this one is reactive component. This is not useful in radiating the energy. Only this is useful. This is radiation resistance. But for impedance calculations, for reflection coefficient calculation, like ZL minus Z naught, in that case we have to use this one also. Okay. This also you have to remember. So what are the things you have to remember for lambda by 2 antenna? That is H bar formula, and radiation resistance is 73 ohm, and input impedance is 73 plus j 42.5 ohm. This much is more than enough. Later on, directivity also I will tell you. I wrote that point in the directivity concept. So students, next quarter wave monopole antenna near ground. So let us take this as a conductor, or otherwise it can be near ground also. That is also taken as a conductor. Okay, like this. And so the length of this is lambda by 4. Now, according to image theory, whenever any conductor is nearby whenever any conducting rod is nearby the conductor surface, then you have to redraw the equivalent circuit using the image theory. Now, this diagram is replaced with equivalent 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 diagram according to image theory is you have to draw here reference line, and then this is the original conductor of shape lambda by of length lambda by 4. Then the image of the conductor, just I am drawing like this, indicating that it is image of the conductor. You can draw like this also, no problem. This is called image. This is also lambda by 4 length. Okay, this is also lambda by 4 length. So now it behaves like a lambda by 2 antenna. So the radiation resistance of this also equal to the 73 ohm only. So conclusion is that lambda by 4 antenna near the ground or otherwise perfect conductor. Ground means earth surface also behaves like a conductor only. Lambda by 4 antenna near the ground behaves like a lambda by 2 antenna, and the radiation resistance of this is lambda by 2 antenna is 73 ohm, you know, but this radiates power only in upper hemisphere. So again it will have half effect only. So again the radiation resistance of this lambda by 4 antenna is you have to take 73 by 2 only. So whatever is there for lambda by 2 antenna, you have to take half of that one. Okay. So here I am writing lambda by 4 antenna near the ground behaves like a lambda by 2 antenna, but it radiates power into upper hemisphere, because bottom side actually conductor is there, only it radiates into upper hemisphere. So it radiates into upper hemisphere. So radiation resistance of lambda by 4 near ground. Even if it is not near the ground also same formula, student. Actually what happens, if lambda by 4 is away from the ground, then it is half of lambda by 2, then radiation resistance is 73 by 2. If lambda by 4 antenna is near the uh, conductor like this, then a very big conductor this one, now the equivalent is like lambda by 2. It radiates as much as lambda by 2, but ultimately it radiates only in upper hemisphere. That is why again the radiation resistance is half of the radiation resistance of the lambda by 2. So in both cases, if lambda by 4 is away from the ground or near the ground, in both the cases radiation resistance is 73 by 2 you have to take. So radiation resistance of lambda by 4 is equal to lambda by 4 is equal to lambda by 2 divided by 2. So that is why you have to take 73 by 2 you have to take, students, right? That is 73 is for lambda by 2 antenna. Now the input impedance of the input Zin of lambda by 4 is equal to, that is Zin of lambda by 2 divided by 2. So Zin of lambda by 4 is equal to this is 73 plus J 42.5 divided by 2 actually, right? Okay. So now coming to the conclusions, you have to remember radiation resistance of lambda by 2. If you want a radiation resistance of lambda by 4 antenna, lambda by 4 is nothing but lambda by 2 by 2. That means radiation resistance of lambda by 4 is for lambda by 2 antenna, it is 73, it will have divided by 2. For example, radiation resistance of lambda by 8 antenna, then lambda by 2 divided by 4, this is so radiation resistance of lambda by 8 antenna is equal to 73 ohm for lambda by 2 divided by 4 you have to take. Then what is the radiation resistance of lambda by 10 antenna? Then you have to go for Hertzian dipole formula, that is 80 pi square dl by l whole square if it is current distribution is uniform. In the question it is mentioned if the current distribution is triangular current distribution, then for if the range is in this lambda by 50 and less than L less than or equal to lambda by 10, for this range you have to take 20. Again below this automatically length becomes very small, then again it becomes uniform current distribution. Again you have to use 80 pi square only, 80 pi square L by lambda whole square. Okay, now here one more note I am writing here. For example, here one conductor rod is there like this, and this is y axis, and this is x axis, and this one is z axis. Now you see this one here at this is theta angle r distance at point r comma theta comma pi, at point r comma theta comma pi. Average pointing vector is equal to half electric field maximum value square divided by eta, it is air medium, so that is why eta naught we have to take, so into ar cap, because wave is going in r direction in this case and power also flows in r direction. This is one formula. So this already you know, half into em square divided by eta naught into ar, and em is maximum value of the electric field, right? Now one more formula is there. Actually this is power density, another formula, that is equal to power density into ar cap also you have to take. Two formulas are there. This power density is nothing but power radiated into gdt divided by 4 pi r square ar. I will explain you this after some time. If total power radiated by this antenna is P radiated, then this antenna has a directive gain. G means gain, D means directive, T means transmitting antenna. We are going to discuss that for that formula also we'll see. So here what happens, let us say 10 watts power is radiated by this, and if this antenna has gain 3, then the 10 watts is increased by 3 times, then it radiates. The radiated power goes radially outward, then it spreads in the spherical volume, then every time it crosses the spherical surface of radius r. For example, at r distance, you have to imagine a spherical surface here like this, then area of this spherical surface is 4 pi r square actually. If r is the radius, then whatever power is there, that means power is power radiated into gain. Actually, yeah, if we transmit 10 watts power, then this antenna has some gain, then it multiply, radiated power is multiplied with gain, and it is spread into this uh, spherical volume. It is sphere, it is not a circle, it is sphere. Then every time you consider one spherical surface, for example, you go to r distance, then you consider spherical surface, then you go and stand there, then this much power will be crossing the spherical surface of area 4 pi r square. So that is why power density at this location is power radiated GDT divided by 4 pi r square. So this is also watt per meter square, and the unit of this also watt per meter square. Actually, this is the average Poynting vector formula in terms of electric field, but this is the average Poynting vector formula in terms of radiated power. Here is the R here. In this electric field, you have seen earlier, but far field, electric field has 1 by R term, 1 by R term. So in this way, here this one, power radiated, total power radiated by transmitting antenna, by transmitting antenna. Next, GDT, D means directive, we will discuss that. Directive gain means direction to direction, that gain change actually. So that is why that is called directive gain of the transmitting antenna. Directive gain of transmitting, TX antenna means transmitting antenna. Now here PD is actually power density. PD means power density. Next, EM is maximum value of electric field, not RMS value, student. Maximum value of electric field. Students, in the antenna questions, if they ask you to calculate electric field, the meaning is maximum electric field only. In antenna questions, if they ask you to calculate the current, that is maximum current. It should be understood like that. In antenna questions, they give 4 ampere current means that is maximum current. It is understood like that. So these are maximum currents taken. Okay. Now here we are about to get one formula. This one, average Poynting vector in terms of power density also written. This is the power density, power radiated into directive gain of the transmitting antenna divided by 4 pi r square, and you equate both of them, then you get the relation between them. So half electric field maximum square eta naught is equal to power radiated GDT 4 pi r square. This eta naught is written as, okay, you can write one more step if you want, then EM square is equal to 2 times eta naught is 120 pi, then power radiated GDT divided by 4 pi r square. Now if you take root of this, first you cancel the terms, pi cancel, 4 into 3 times. So 30 into 2, 60. Okay. Then power radiated, then derivative gain, root for this divided by R. So this formula you remember. If you don't have patience to remember this formula, then you equate these two time to time, no problem. That is also. So it is better you remember them, and so that at any time you can write this. It depends on your patience, students. So this formula, and this is also formula. So magnitude of average Poynting vector gives power density. Okay. Here, if they ask RMS value, then this is a maximum value, remember, then RMS value is equal to E maximum by root 2 you take. Don't remember formulas for RMS also, maximum value also. Only one formula you have to remember. Then if they ask you RMS value, then you have to take maximum value by root 2. They will not ask, they will ask electric field, means here only maximum electric field. Right, students? Now in exam questions, they give power radiated, they give derivative gain, they give distance, and they ask you at 100-meter distance, 100-kilometer distance, what is the electric field value. Then here you have to put 100 km. Okay, right. Right, students. Antenna characteristics. First one is radiation pattern. So radiation pattern means shape. Radiation pattern means in which direction antenna radiates, and what is the value of the electric field, what is the shape of the electric field, what is the shape of power pattern. We have to see those things. Pattern means shape actually. So this radiation pattern has actually field pattern, that means electric field pattern, and power pattern. Okay. So field pattern means electric field. Now field pattern. That means field pattern means shape of electric field. Shape of electric field with respect to theta comma pi. With respect to theta and pi. With respect to vertical angle and horizontal angle is called field pattern. So here electric field is there, one parameter. Horizontal angle is there, pi, that is second parameter. Vertical angle is there, that is third parameter. That means here it is 3 dimension. But board is how many dimension? Only 2 dimension. That is why 2 dimensions one time, 2 dimensions other time drawn. Then they are superimposed one upon one. Then we get the 3-dimensional field pattern. So here electric field is a function of theta comma pi, right? Now electric field versus theta. Electric field versus theta. Theta means what actually? Vertical angle. Plot is drawn by taking pi constant, because on 2D board at a time we can draw 2 variable diagram. Electric field is one variable, theta is another variable. Okay, plot is drawn by taking pi constant. Then this plot is called as, E-plane pattern. E-plane pattern. Here E means not the electric field. E means elevation plane, because theta is called elevation angle. So that is why elevation plane pattern or otherwise it is called vertical pattern, because vertical angle, no, that is why vertical pattern, vertical pattern. Okay. Now E versus pi plot is drawn by taking theta constant at particular theta you have to do. Then this plot is called as then this plot is called as H plane. H means horizontal, because here horizontal angle is varied, so that is why it is called H plane pattern. Okay, so it is called H means horizontal here. H plane pattern or horizontal pattern. Now field pattern is superimposition of E plane and H plane patterns. So that is called field pattern, because I told you here na the shape of electric field with respect to theta comma pi is called field pattern. So electric field is a function of theta comma pi. So total 3 variables are there, but both these 2 dimension. At a time we can draw 2 variables on the board. So that is why electric field, how it changes with respect to theta, then by taking pi constant is taken. So with respect to theta you are seeing means that is vertical angle, so it is called vertical pattern, or otherwise that is also called elevation angle, so it is called E plane, elevation plane, vertical plane, that is the meaning. Similarly, E versus pi plot is drawn by taking theta constant here, so you are changing horizontal angle, that is why it is called horizontal pattern. So H plane means horizontal plane here. Then you superimpose one upon one, then that is called as a field pattern. So combination of vertical pattern and horizontal pattern is called as field pattern now. Okay, right. So combination of E plane comma H plane pattern is called as simply field pattern. Field pattern means electric field pattern here. Anyway, this theory is not important. Just I am telling you what is happening here. So electric field can be generally a function of theta and pi. So at constant distance we will be observing electric field. Actually what we do, student, field pattern means the here antenna is there. You go to particular distance, then fix the distance constant. Then at that distance you keep changing the horizontal angle like this, and you see the electric field values, and keep changing the vertical angle like this, then you see the electric field value, draw the plot, that is called the field pattern. Now first one we will draw that case 1. Anyway, before drawing what we will do, let us draw the let us write the equation of at far field for Hedgian dipole antenna, H pi s is equal to, this is I naught dl sin theta divided by 4 pi j beta divided by r e power minus j beta r. So E theta s is equal to eta into h pi s, you have seen. Now I told you to remember this equation. We are drawing the field pattern for the Hedgian dipole antenna here. So E theta s is equal to, now eta I naught dl sin theta divided by 4 pi, right? Multiply with theta, sin theta, 4 pi, j beta divided by r, e power minus j beta r. Students, this is written like this. E theta s is equal to modulus I will write. If you take mod of this, what will happen? 1. And mod of j is also 1. Now that is equal to eta I naught dl and beta divided by 4 pi r into sin theta. Actually, whenever theta is equal to 90 degrees, this has highest value. That is why it is called maximum electric field. This is called maximum electric field. Okay. So, at theta is equal to pi by 2, electric field has maximum value at particular distance, because I told you here we are not bothered much about the distance. Actually, no, if you take antenna, in which direction it has more radiation, that means that is our importance. In which direction it has more radiation means you have to see the radiation with respect to the angles. Actually, that is why angles are given importance. So at theta is equal to pi by 2, electric field has maximum value. Now that is why modulus of E theta is written as Em into sin theta, right? Now, normalized electric field is defined like this. Normalized electric field. Normalized electric field is En is equal to electric field divided by maximum electric field is called as normalized electric field. So, electric field divided by maximum electric field is defined as normalized electric field. So, now in our case that is normalized electric field is equal to here E theta s divided by okay. So, E theta s divided by Em. Now, that is E theta s is this one, eta I naught dl, or otherwise directly I have written here, and E theta s by Em gives sin theta, that is equal to sin theta. So these are all not important, student. What discussion is going on here? These are all not important. Just a sequence we are following. Actually, what they do in textbooks, they maintain this at particular distance. They observe the value, but their focus is to, if there is antenna in at this much angle, what is the electric field intensity at this angle, at this angle, at this angle. So for these locations, you have vertical angle also and you have horizontal angle also here. Both are there. With respect to angles, how electric field changes, that is drawn here. Now, what is important is normalized electric field magnitude is proportional to sin theta. Okay, right? For a Hessian dipole. Now you take different angles. You take different angles, and theta is equal to 0 angle. Theta is equal to pi by 2 angle. Otherwise, you can take 45 also, no problem. You can check different, and theta is equal to 90, and theta is equal to 3 times pi by 4. Okay, and theta is equal to 180 degrees. So sin theta value, sin 0 is what, students? 0. Sin pi by 4 is 1 by root 2. Sin 90, that is sin pi by 2, is equal to 1. Sin of So this is nothing but 2 times pi by 4, that is pi by 2 plus pi by 4. So sine is positive, second quadrant once again it is 1 by root 2. Then sine pi, it is 0 actually. Now it is very simple. So Hertzian dipole was like this. Okay. Otherwise no need to take Hertzian dipole. Later on I will take. Here na first plot is electric field normalized versus theta, because we are changing the theta at pi is equal to constant. We will take pi is equal to 0. Okay, I will write there pi is equal to 0. Can you tell me what is the meaning of pi is equal to 0? So pi 0 means horizontal angle 0. So where that horizontal angle 0? XZ plane. XZ plane. Yes, that is correct. If you want draw a diagram, so see this diagram. This is x-axis. This is y-axis. This is z-axis. Now pi is angle between x-axis and row line. Now here, if you take row line here, then angle pi is equal to 0 here. Now you can take this row line on the xz plane. You can see here, this is x-axis, this is y-axis, this is z-axis. So if radius line is on the x-axis, then angle pi is 0. You can take this radius, you can lift this line like this, but now also angle 0 only. So horizontal angle is 0, student, here. So this is x-axis, this is z-axis. On the xz plane, horizontal angle is constant. So pi is angle between x-axis and row line. Pi is equal to 0. You can see here I am drawing like this. So like this lines you draw, all of them are on xz plane only. You can see all are on xz plane only. So that for that pi is 0. So pi 0 means xz plane. Okay, students, pi 0 is xz plane. That means here we are going to draw the electric field value, that is En value is sine theta actually. You have to draw En versus theta. You keep changing the theta. How electric field value changes you have to see, and for constant pi. So pi 0 we have taken, that is xz plane. Now you see this one, x-axis I am taking here like this, x-axis, and this is z-axis. So xz plane, automatically this one will be negative x-axis. So anyway, xz plane we are drawing, students. Okay. Now at pi is equal to 0, theta is equal to 0, and electric field value is 0. At theta is equal to pi by 4. So I will draw the lines like this. Pi by 4 means 40, 45. So like this. So this is theta is equal to pi by 4, and this z axis is nothing but theta is equal to 0 on the z axis. Now what else, students? Theta is equal to pi by 2 means this one. This is actually x axis here. X axis, I will draw here x axis, students. I will write here x axis for this theta is equal to 90 degrees. Now draw a line here, and this one theta is equal to, what do you say, 135 degrees, that is 3 pi by 4. 3 pi by 4. This one is vertical angle, theta is equal to 180 degrees, that means pi radians. If you draw this side, then we want modulus of this En is sine theta, modulus of En becomes mod sine theta. So if you draw the plot this side also it is symmetric, actually symmetric. Now it is very simple. What you have to do is, for example, uh, 90 degrees na, whenever theta is 90 degrees na, sin theta value is 1. So you take 1 unit here. Assume that this is 1 unit. It is actually scaling is done. So it is 1 unit. Now 1 by root 2. So 1 by root 2 value, and this is 1 by root 2 value at 135 degrees also. Here also 1 by root 2 value. So here 0 value is there. So it will be coming like this actually. It will be coming like this. So here also it is symmetric actually. Okay. Plot is symmetric. Here it has maximum value. Okay, student. This is the plot. It is called figure of 8. It is looking like 8, na? 8. So it is called figure of 8. Figure means diagram. This diagram looking like 8 number. So figure of 8. Here what you have to remember, students, one thing you have to remember. Now if you take the antenna rod, in this Hertzian dipole antenna was here. Hertzian dipole antenna was here. Antenna. So you have to remember, after doing this much analysis, you have to remember electric field configuration in the elevation plane shape is figure of 8. That is one point. Second point, this is the maximum radiation. This maximum radiation is this is the antenna rod that is perpendicular to the maximum radiation is perpendicular to the length of the antenna rod. This you have to remember, students. For example, like this antenna, then the configuration is like this. So if antenna is like this, then perpendicular to this rod you have like this. That's what you have learned from this. Okay, if this antenna rod, then field pattern is figure of 8 and maximum electric field is 90 degrees to the length of the antenna. Okay, now that's what you have to remember, students. So here second one, if you see na, second one, normalized electric field versus horizontal angle at theta is equal to 0 we will try to take, but if you take theta 0, sin 0 is 0, there is nothing to observe actually. So there is nothing to observe. That's why you take theta value in such a way, because of theta this function doesn't become 0. Then if any some other variable is there, you can observe variation with respect to that. So here theta is equal to 90 we will take. So this is constant actually. So theta is equal to constant we have taken. We are drawing the electric field normalized plot with respect to angle horizontal angle pi at constant theta. But you may ask question, sir, here there is no pi at all, then what are you drawing? Yes, that is also drawing. You should understand that means even though horizontal angle changes, the electric field value is not changing. That means that antenna is able to maintain constant electric field. It is able to radiate constant electric field for entire horizontal angle. So that is the meaning of that one. This also they ask an objective question. You will see circle. I will tell you after drawing. Let us not waste time. Theta is equal to pi by 2 means the meaning is xy plane. That is xy plane, or otherwise that is called horizontal plane. On the horizontal plane only you are going to change the horizontal angle. So xy plane. You know that, my dear students. Here, if you want, you can see here. This is z-axis. Angle between xy plane and z-axis is 90 degrees. So, or otherwise from the z-axis in every direction you come 90 degrees, then you will get the xy plane, students. So that means here we have to draw xy plane plot actually. Xy plane plot. So here we will be taking first what I do. Anyway, it is one only, na. So electric field Normalized electric field value at theta is equal to pi by 2 is 1. So it is constant. So for any horizontal angle, this electric field value is 1 only. So there is no problem at all. XY plane you take. So this is actually x-axis, students. We are taking. For this also here x-axis is there. And this one is y. And this one is minus y. And this is minus x. If you see the angle between the x-axis and rho is 0, then on y-axis it is 90, then opposite to the x-axis, that is 180, opposite to the y-axis 270, again 360. Let us draw here. This horizontal angle here is 0, and here horizontal angle on the y-axis is actually 90 degrees. That means here horizontal angle pi is equal to this is a so this is 0, 90. Okay, this one is 180, and again here horizontal angle is 270, and again just near this horizontal angle is again 360. So 0 degrees and 360 degrees both are same. Even whatever might be the value of horizontal angle, electric field value is same. Electric field value is same. So it looks like a circle. It looks like a circle. That means value is 1. That is the meaning. Value is 1. It is a circle. This side also 1. This side also 1. Here also 1. Here also 1. This is also objective question, student. So objective question, how they will ask, electric field pattern is a circle on, answer, xy plane, student. XY plane. Now what you do now? See, students, you assume this is y-axis, this is x-axis, this is y-axis, this is x-axis. Now they are like this. Okay. Now tell me, what is this axis? I am holding like this. This is axis is which axis? X-axis. This one y-axis. Now here is which shape? Circle. Now you take that here. This is which axis? X-axis. That is z-axis. Then out of the board is y-axis. So this circle diagram you turn here like this. Now this is x-axis, this is y-axis. That means on the horizontal plane this pattern is like a circle like this. Now if you superimpose them one upon one, then electric field versus theta comma pi plot is like this. So if you superimpose them, this is actually x-axis and this one is z-axis. Out of the board is actually y-axis. So here this is x-axis, this is z-axis. Out of the board is actually y-axis, and ultimately here you have like this. Okay, and here there is a circle like this. Circle. This is y. That circle is there now, coming from back side like this. On the board you have to draw like this only. So like this field pattern is there. This is called donut shape. DOUGH-NUT. Donut shape this is. So donut shape. Right? So this is the overall electric field pattern. This is X, this is Z. So you remember these two separately. If antenna is like this, then 90 degrees to the antenna length, we have figure of 8 shape, and automatically this, if they ask the question, the antenna rod is like this, then 90 degrees to that antenna rod, here you draw a circle on that plane, that means horizontal plane, electric field value is actually constant, right? Next, let us talk of power pattern. You know, student, normalized power is proportional to normalized electric field whole square. Okay, normalized power is proportional to that normalized electric field is sine theta, so it is sine theta whole square. If you draw the sine square theta versus theta and pi, then that is called power pattern. That is called power pattern. Pattern means shape actually, right?